Sever. I'm coming from Danfoss, like also other colleagues, Ekaterini, KRIEZI. She is our thermodynamical specialist. Lars Larsen, he is leading PEC controllers for CO2 systems. And I was in this project during this year. I worked on specification of what is a new system and how it should work. As a small introduction to this topic, CO2 started in Europe like 15 years ago, and at least these applications, what we were following in Danfoss quite a lot, was these food retail applications, and most of applications were dominated on the market in that time between 100 and 300 kilowatts. And obviously all the technology components and everything start developed in this range, compressors and everything. And for the last couple of years, this technology is looking to go in two directions. One direction is, like my colleague explaining, more to the industrial refrigeration, so to the bigger systems. Today we have bigger compressors, bigger pipes, bigger valves. But also it goes in direction to the smaller systems, smaller compressors and everything. And with this paper and this application what we developed and the injectors, we are looking how to make these smaller systems more efficient. What is small? This is a big question. In this paper, we look at systems between 40 and 70 kilowatts because they are fitting to this ejector, what we will talk about later. So, commercial refrigeration systems. What is commercial refrigeration system? It is a system with multiple evaporators, so 10 plus evaporators. It's not a single evaporator like it is on the picture. So, we have three different kinds of ejectors. High pressure lift ejector, liquid ejector, and also low pressure lift ejector. The difference between them is, of course, low pressure and high pressure are special for working with gas or vapor, and liquid is for liquids, obviously. But the difference between the low pressure and high pressure ejector is how much it can lift gas and what is the entrainment ratio. Entrainment ratio is a ratio between how much you can suck and how much is entering as a motive flow. And these ejectors can do low pressure lift, but high entrainment ratio. To explain the system, I will start with the system where it's cold ambient. It consists of medium temperature compressor, so this is on the high stage. It goes to the gas cooler. After the gas cooler, it goes to the ejector. Now, ejector in this mode of operation works as a normal high pressure expansion valve. You are entering to the receiver where you have separation of liquid and vapor form. Liquid goes to feed empty and LT evaporators. When it goes out of evaporators, it goes to LT, goes to the LT compressors. Empty goes to the suction of empty compressors. Here is check valve. I will talk about this check valve. It is important in this system. LT compressors are discharging after this check valve. And then, of course, we have gas bypass line. In this system, we are controlling the pressure in the receiver with what we call as a pressure difference algorithm. So the pressure is controlled between this point here in the receiver and what is the pressure out of the empty evaporators. And in this example, we are controlling with the 3 bars pressure difference. So you have here in empty evaporators 26.5 bars, and in the receiver is 29.5 bars. Why 3 bars? Again, we are talking about smaller systems. And if we have a lower pressure in the receiver, we can utilize more work from ejector. Why not lower? Because in these lines you have also pressure drop, you have filters, you have expansion valve, you have also distributors in the evaporators, and then you have to spend these 3 bars in the system, in this distributed system. All in all, like it is here, it works like a normal standard booster system, and only with one gas bypass valve. So this one is controlling pressure in the receiver. The second one is not working. If you look another side, I mean, when it's warm, this is example of 35 degrees temperature out of the gas cooler. If you are controlling pressure in the gas cooler in the optimal way, it will be around 90 bars in the gas cooler. So at that point, we are able to make suction. So you can utilize this ejector to take all flow which is coming from the empty evaporators, and we are taking all flow and delivering through the ejector to the receiver. By doing this, because we have the ejector with a high entrainment ratio, we can take all the flow, but the lift, what we are gaining is now something like 5.8 bars between this point here and this point here. And system reacts automatically that the pressure in the receiver is becoming higher because of the work of ejector, and the gas bypass valves start to open, and you will see at the end of the presentation they will open completely, equalizing the pressure from the receiver to the suction of empty compressors. Because here we have now higher pressure, the check valve will close, and LT compressors will discharge gas to the higher pressure than it was before. Those who understand the parallel systems, they can notice that now empty compressors are working like a parallel compressors because they are taking gas from the receiver, so from the higher pressure. And we are definitely improving the system in empty side, because now empty compressors will work from the higher pressure, but LT compressors will have a higher pressure to make it. So this is why we did this analysis, to analyze how big is the influence of these LT compressors and how it will work through the year. What is the benchmark system? It's a standard system, so CO2 system. We didn't compare with other refrigerants because we don't wish to compare different systems, but CO2 booster system with the same constant pressure difference control, I mean this pressure in the receiver. Design cooling load for empty and LT is specified for the ambient temperature of 32 degrees, and we used cooling load variation with the ambient temperature according to SEPR standard. It means this is the line for the empty load, and this is the line for the LT evaporator loads. So it varies, the load varies according to the ambient temperature. Then we looked at a different system. One system is only empty, 50 kilowatts, and another one is empty, 50, LT 10 kilowatts, and the third one is 50 empty and 20 kilowatts LT. Okay. Temperature out of the gas cooler, yes, so this is also what Professor Hrnjak was telling. So this is the line, how we are looking what is the temperature out of the gas cooler depending on ambient temperature. So the temperature difference is not the same in the winter time and we are in subcritical, and also in the transcritical area where we are working with the only 1 to 2 kelvins temperature difference. Here we are at 7 to 8 kelvins. What is the outcome? If you look at this graph here, you will see this blue line shows the pressure lift from ejector. The area until the 17, 18 degrees Celsius, we didn't use in this simulation because until this 18 degrees ambient temperature, simply the pressure lift is not higher than 3 bars, so we are working system with the standard system. Values which are between 35 and 40 degrees Celsius, here we have some questions, but we will explore why, not in this paper, but in some others. In the COP line, it looks like this. From this point, we do this improvement of COP. The dotted line is a standard reference system. What is maybe the most important graph, at least for me, is this energy reduction, what we noticed for different systems. So again, until 18 degrees, nothing is changed. But here, if we have an empty only system, we are gaining something between 14 and 16% energy reduction comparing to this benchmark system. And of course, if you have a more and more LT load, so this is with the 10 kilowatts LT, the efficiency is, or energy reduction is reduced because of course you are jeopardizing efficiency of the LT compressor. This is logical, and also if you go to this 20 kilowatts, it's even less. Then we make this SCPR calculation for 5 different systems: Zagreb, Belgrade, Athens, Rome, and Madrid. I used these temperatures from PEC Calculation Pro. So these are these reference years. And we did this is the number of hours per year with certain temperature. And then you can make this calculation, so SCPR and also energy demand calculation. And to make it a bit easier to understand what is happening, you can see what is the improvement of seasonal energy performance. And on the right side is annual energy reduction. So, of course, it depends on how much hours you are in this ejector mode. You will gain, of course, more energy reduction. So, logical, in Athens we got the highest values, but also Zagreb and Belgrade are also not bad. All this analysis is taking into account if you don't do heat recovery. If you do heat recovery, then the number of hours when you will use ejectors will go again to the whole year for heat recovery time plus all this ambient temperature above 18 degrees Celsius. Laboratory tests. So these are time span of 6 hours. So we looked how the system was changing between these two modes of operation and what we are gaining this pressure lift. So we increased the pressure in the gas cooler by changing the temperature difference to the ambient temperature. And then on the right side you can see that we slowly increased this pressure lift in a controlled way. What you can see here is a time span of 1 hour. Where you can notice, and this was also interesting for me to look at this change of system between the standard mode. So if you look this black line, this is the pressure in empty evaporator and what is the suction of empty compressor. And then when we change the reference in the receiver, and by doing this we are allowing that low pressure ejector start to work, then we have this transition period when the system was kind of fluctuating between the ejector mode and the, let's say, standard mode. And then after, let's say, 10 minutes, it stabilized in an ejector mode of operation. So we have here like 5 bars pressure difference. This dotted line shows the opening degree of the gas bypass valve. So you see it has kind of sudden increase increased and dropped, so this was causing this transition period to stabilize operation, and then both of those valves opened completely, so to 100%. And what is also nice to see that when we on purpose wish to put system out of ejector mode, and this is by increasing the reference in the receiver, this stabilization period after this moment, it takes like a minute or two maximum, and then the system goes again like a standard system. Conclusions, we tried with this system to make it a bit simpler and use this ejector technology in this kind of installations. We don't need parallel compressors, which as a default is a more expensive solution. We show that with ambient temperatures higher than 80 degrees, we can achieve these benefits. It's also important to understand this ratio between the LT and empty load, how much this can impact in energy reduction. And, well, all in all, it is it's quite a nice small system. So, any questions? Or at the end.
Thank you, Mr. Sever.